Hi everyone, I'm Armando Angrisani. I'm a second year PhD student at Sorbonne University in Paris, and today I'm gonna present our recent work about differential privacy amplification in quantum and quantum-inspired algorithms, in collaboration with Mina Doosti and Elham Kashefi. Differential privacy is a theoretical framework for privacy-preserving data analysis that has been introduced in 2006. There are already several works relating differential privacy to quantum computing. For example, differentially private quantum channels have been defined, as well as differentially private quantum measurements. Moreover, we have some application to robustness to quantum adversarial attacks, quantum stability, and improved quantum shadow tomography. In privacy-preserving data analysis, we want to perform a computation on a statistical dataset and then release the output. We have an extra requirement, that is the privacy requirement, that says that similar inputs should be mapped to epsilon-close output distributions. But how we define closeness? One popular choice is the Rényi relative entropy, that is parameterized by a parameter alpha between 1 and infinity. And remark that for alpha equal to 1, we obtain the relative entropy, that is the Kullback-Leib divergence, and for alpha equal to infinity, we obtain the max divergence. Given that, we can define Rényi differential privacy. We say that two datasets x and x prime are adjacent or neighbors if they differ in at most one entry. Then we say that a randomized algorithm A is alpha epsilon Rényi differentially private if for any pair of neighbor inputs we have that the Rényi divergence between A of x and A of x prime is upper bounded by epsilon. In a similar fashion, we can also give the definition of the standard differential privacy. We say that A is epsilon delta dp if for any pairs of neighbor inputs and for every subset f of the possible outcomes of A, we have that the probability of A of x being in f is upper bounded by e to the epsilon times the probability of A of x prime being in f plus delta. We also remark two basic facts, that is that epsilon 0 differential privacy corresponds to infinity epsilon Rényi differential privacy, and moreover that Rényi differential privacy always implies approximate differential privacy. Some of our results can be regarded as a quantum analog of privacy amplification by subsampling, a celebrated classical result showing that running an algorithm on a uniform subsample amplifies privacy. A similar phenomenon happens when a quantum algorithm receives as input a quantum encoding of a classical dataset. The magnitude of this effect is captured by a parameter that we dubbed kernel privacy. The level of privacy coming from the encoding alone is not sufficient for many applications, and for this reason we need to combine it with a further source of privacy, namely a noise adding mechanism. Let's consider the following simple algorithm. We start with a classical dataset X, we encode it in a quantum state ρ, we apply a binary measurements M, and we store the output in a bit Y. Then we add some noise to Y, which is usually sampled from a Gaussian or Laplace distribution. We can show the following theorem. So let's say that ρ has kernel privacy gamma, we put some restriction on the distribution P, which we state here in terms of D1 divergence, that is KR divergence, and then we show that the algorithm is 1 gamma epsilon Rényi differentially private. This is a simple case because we are dealing with D1, then we can use the joint convexity of relative entropy to show it. In the most general case, joint convexity doesn't hold, and then we have to use some technical lemmas that holds under mild conditions. We can also show a similar statement for approximate differential privacy. In this case, we need m to be larger than 1, that is, we need to iterate several times the measurement and then take an average of the outcomes. On top of this average, we have to add our noise adding mechanism. In the present case, let's say that the noise is coming from a Laplace distribution. We can then show that the algorithm is epsilon delta differentially private, and the proof consists mostly in conditioning on the mean being concentrated around the expected value, and then invoking the Chernoff Ofting bound. Then we also have an analogous amplification result for quantum inspired sampling. Let's consider a classical dataset X encoded in a quantum state via an amplitude encoding. Then, if we measure this quantum state in a computational basis, we obtain a point coming from a quantum inspired sampling. We also remark that this kind of sampling can be also performed with a purely classical hardware, and this is why it is called quantum inspired. We can say that quantum inspired sampling is a generalization of uniform subsampling, and it also provides a privacy amplification. We can also recover the result for the uniform subsampling case as a special case of our theorem. Finally, we extended the work of Zhu and Hing that used the notion of neighbor quantum states based on closeness in trace distance. In particular, we show that unitality combined with contractivity in trace distance provides quantum differential privacy. Moreover, we show that the sequential composition of noisy quantum channels amplifies quantum differential privacy. This can be regarded as a quantum analog of privacy amplification by post-processing. Our results readily imply generalization and adversarial robustness guarantees for quantum machine learning. Future directions include experimental tests of robustness to adversarial and privacy attacks on noisy quantum classifiers. I thank you for your attention and remind you that you can find our work on the arXiv.